This is an illustration of a heating curve for water. So here's the temperature increasing up the y-axis, heat being added across the x-axis, but now we're actually having some numbers in here. So this is for 1 mole of water. So to heat the water from negative 25 degrees up to 0, heating the ice takes 0.94 kilojoules per mole. Well, how do they figure that out? Q equals mc delta T. Okay, so that one's going to come back. So that's a Q equals mc delta T. So if we've got 1 mole, we have to calculate the mass of that. We need the specific heat capacity of ice, which is not exactly the same as water, and we need the change in temperature, which would be final minus initial. Final is 0 minus negative 25, so plus 25. And that would give us this much kilojoules per mole. The next thing that would happen as you're adding more heat is that 1 mole of water is going to melt. So that's this one. Melting from a solid to a liquid is going to take 6.02 kilojoules per mole. That's the heat of fusion. So that's delta H fusion. So we call this a heating curve, but it's not exactly a curve, is it? It's a series of lines. To calculate the amount of energy needed for each of these lines, each line has an equation that you use. The ones that are slanted, changing temperature, those are Q equals mc delta T. The ones that are horizontal, that's changing state, and that's going to be heat of fusion or heat of vaporization. So this is the heat of fusion, and then going from 0 degrees Celsius up to 100 degrees Celsius, that's going to be Q equals mc delta T again. But we can't lump these two things together because the heat capacity of water is not the same as ice. When we get it to boiling, then we're going to have another horizontal line, and we calculate that energy using the heat of vaporization. And once it's all turned into steam, the steam can get hotter and hotter, and that again is Q equals mc delta T. But now this is the heat capacity of the gas. Okay. So there will be a problem on the exam that asks you to calculate part of this. I'm not going to make you do this whole thing. It's rather tedious, but to do part of it. And we'll see that in these examples. This is a conceptual question, though. You just saw that the heat capacity of ice is 2.09 joules per gram degree Celsius, and that the heat of fusion of ice is 6.02 kilojoules per mole. When a small ice cube at negative 10 degrees Celsius is put into a cup of water at room temperature, which of the following plays a greater role in cooling the water? Is it the warming of the ice from negative 10 to 0, or is it the melting of the ice? These are kind of hard to compare because this is per gram and this is per mole. But look at the difference in unit here. Kilojoules. That's about 1,000 times more than the other number. So the heat of fusion, melting the ice, is going to take a lot more energy. So it's the melting of the ice that actually is doing most of the cooling of the water. Any questions? Calculate the amount of heat needed to take 1 mole of ice at negative 25 degrees Celsius to steam at 125 degrees Celsius. I'm going to change this one a little bit. Because this is that whole stupid problem. Let's go to water at room temperature. I recommend drawing a little heating curve for this, just to help you see what's going on. So we're starting down here at negative 25, and we're going to heat the ice up, and the temperature is going to stop increasing at 0 while the ice melts. And then the temperature will rise again. It'll keep going until it gets to 100, but we only need to get to 25 degrees Celsius. So I have 3 separate lines here, so I'm going to calculate the energy for the 3 separate things and add them together. So the slanty lines where there's a change in temperature, you use Q equals mc delta T. So I'm going to call that one A, and this one B, and that one C. So for the first line, Q is equal to the mass of the water, of the ice, times the specific heat capacity of the ice, times the change in temperature of the ice. Well, it's 1 mole of ice. What's the mass? Use the molar mass of water, and so that's 18.02 grams. So here the energy Q is equal to the mass, 18.02 grams, times the specific heat capacity. This is the ice, and so we need to use C for the ice, 2.09 joules per gram degree Celsius. And then the change in temperature. Final minus initial, we're going from colder to warmer. The final is 0. 0 minus negative 25 is plus 25. So we can calculate that. And these are the sorts of calculations we did back in chapter 7. So I'm getting 941.545 joules. So the grams cancel and the degrees Celsius cancel. I'm left with joules. So that would probably be 2 sig figs because of the temperature. The next part here, this represents the melting of the ice. So we're not really using an equation here. We're using a heat of reaction, essentially. We want the heat of fusion because the water is fusing, it's melting, the ice is melting. And so this is this many kilojoules per mole of water. So if I have exactly 1 mole of water, and I multiply by 6.02 kilojoules per mole, the moles cancel out, and I've got 6.02 kilojoules of energy. And then the third line is Q equals mc delta T again. But this is liquid water, not ice. So the mass is the same, 18.02 grams. Specific heat capacity is 4.18 joules per gram degrees Celsius. And what's my change in temperature here? The final temperature minus the initial temperature. It's 25 again. (18.02 plus 4.18, not plus, times 25. And that's probably also going to be 2 sig figs because of the temperature. So we just calculated the amount of heat needed to get from here to here, from here to here, and from here up to there. Now we're going to add them together. But we need to be a little bit careful because this one is in kilojoules. So let's convert these guys to kilojoules. You do that by dividing by 1,000. So this is going to be 0.9415 kilojoules. And this is going to be 1.883 kilojoules. So I'm going to take this one, and this one, and this one, and add them together. Calculator's giving me 8.8445 kilojoules. And here I'm adding, so I'm looking for the number with the fewest decimal places. This one has 2 decimal places, this one has 2, this one has 1. So this is going to be limited to that decimal place, 8.8 kilojoules of energy to melt the warm up the ice, melt it, and heat it up to room temperature. Any questions? There's a lot of calculations in here, but each of the calculations is simple, right? Q equals MC delta T, moles times heat of fusion or vaporization, and then add them together. Yeah.
Are the 2 sig figs from the temperature?
The 2 sig figs are from the temperature, yeah. And this is not the type of problem where I'm going to try to trick you with sig figs, right? But we should always try to use at least a reasonable number of significant figures, because rounding them off too much will get you the wrong answer. And carrying all the digits can be super, super tedious. We don't want to do that either.